Okay, this is going to be a video solution to the practice quiz that I wrote in spring 2022, I believe. So this is the one that's listed as 5B on Canvas. So we have a seesaw here with a child sitting at one side, and the child's mass is 30 kilograms. And we also have the seesaw bar, which is 10 kilograms. And then we have this rope that's attached to the left side. There's a pivot, and so a bunch of forces acting here, but we know that it is at equilibrium. So whenever we see at equilibrium, that tells us right away that the torques and the forces are balanced. So both tau net and F net are equal to 0. So we'll be able to use all that when we solve the problem. So number 1 asks us in the space below to draw an extended force diagram containing all the forces acting on the seesaw plank. Okay, so not on that picture, so we'll have to draw a new seesaw. So this is our seesaw plank, and we just want to place the forces that are acting on it where they're acting on this plank. So I guess going from right to the left, on the far right, we have the child sitting at the end. So there will be a force due to gravity on the child on the plank. So we'll have one force that's acting downward there. We'll call that Fc for F child, and that is perpendicular to the plank, straight down. Then we have, well, we're going to have a pivot force due to the pivot of the seesaw, but we're not quite sure where that's going to point yet. So I'm going to leave that for now, and we'll come back to it. We also just have gravity acting on the seesaw itself, on the plank. So that'll be right at the center of mass. So halfway through, we'll get some Fg. So that's the force of gravity acting on the seesaw plank itself. And then finally, we have the tension force, which acts at the far left and points down to the left like this. And we know that the angle that the rope makes with the ground is 30 degrees. So maybe the more useful angle would be the angle between the rope and the perpendicular plane to the seesaw. So we know this angle is 60 degrees, the one I'm just labeling right there. So that's not part of the question, but that will help us later on. So we have this 90 degree, this right angle, this right triangle right here. 30 degrees is the bottom left angle in it, and 60 degrees is the top one that I've labeled. So now we have our pivot force, and that's going to act about right here. And so we need to decide what direction to draw the pivot force. And the thing that we're going to use to figure that out is the F net equaling 0. Because we know the pivot force can't impart any torque because the r, the distance between the force from the pivot point and the pivot point itself, is 0. So there's no torque, and the force is just going to be whatever it needs to be such that the net force is 0, because we know the plank isn't moving anywhere, there's no net force on it. And so if we look at what other forces we have here, all three of them have a component that is down, right? None of them has an upward component. So we know that the force from the pivot is going to have to point up. It's going to have a positive y component. And then also, Fg and Fc, the forces due to gravity, don't have any x component, but this tension has a negative x component, or it points to the left. So this pivot point is going to have to counter that in order for the x component to become 0. And so we're going to have a pivot force that goes up and to the right. So this will be our F pivot. Again, up to balance all the downward components of these three forces, and to the right to balance out the leftward force of tension. And none of these are obviously to scale, but they give a rough idea of what we need. So that's our extended force diagram. Now let's get into the meat of the problem solving with part 2, which asks us what the magnitude of the tension in the rope is. So now we're going to go to our torque balancing, meaning that our net torque needs to be 0. And just as a general tip, I would say to always start with torque balancing. So this extended force diagram tells us how to do that, since it labels where all the forces act and then gives us what their moment arms or their r vectors are. And so we'll start with the tension. So tau net equaling 0 just means that the torque that goes into the page has to equal the total torque that goes out of the page. So let's first identify here which of these forces produce a torque in and which of them produce a torque out. So if our pivot point is this blue dot here where I've drawn F pivot, and I'll mark it with green just so we can see that's our pivot point, then we have two different directions that the seesaw could tilt. It can either go counterclockwise like this or clockwise like that. But that's not the direction that we associate with torques, right? We want to know into or out of the page. So if we use our right hand rule, we can see that the counterclockwise direction, and I encourage you to try this along with me. If you wrap your right hand in the counterclockwise direction, you'll get that that is associated with a torque out of the page. And oppositely, if you wrap your fingers clockwise with your right hand, you'll find that your thumb points into the page. So the torque is into the page. So now to see which of these forces produces a torque into and out of the page, we'll just see which ones produce these counterclockwise and clockwise rotations. And since Fg and torque both want the seesaw to rotate counterclockwise, those are going to be on the tau inside, right? So I'm going to put Fg and torque over here. And then the force due to the child is on the right-hand side. That one wants the seesaw to rotate clockwise. And so that's going to be associated with tau out of the page. So now we've identified where all our forces act, and we see gravity and tension produce a torque in one direction, the force from the child produces a torque in the other, and they have to balance out. So now we can write out our torque balancing equation. So I guess the intermediate step would be saying that the torque from gravity plus the torque due to tension have to sum up in magnitude to the torque from the child so that all our torques balance in and out. And now we can expand each one of these things. The torque due to gravity, well, each one of these, we know that torque is equal to F perpendicular R, or is also equal to R perpendicular F. Gravity is already perpendicular, right? It's R vector. I'm going to draw it in black right here, just points from the pivot point to Fg. We'll call that Rg, right? That's already perpendicular. So tau g is just going to be Fg. Let me switch back to blue. Is just going to be Fg times Rg. And now we have the torque due to tension. Now this one is a little trickier because the tension is not perpendicular, right? We have our R vector that points from the pivot to the tension, but then the tension has both a perpendicular component, so this would be our tau perpendicular, and a horizontal component, a parallel component. I call that tau parallel, even though we don't need tau parallel. So if we want to calculate what the tau perpendicular is going to be, we need to use trig. So we'll still have our Ft, or sorry, we just called it T. So we still have our tension force times RT, the distance away, but now we need that piece that gives us only the perpendicular. And so if the angle is 60 degrees that I've labeled right here, then tau perpendicular is going to come from cos of 60 degrees. So because that's the adjacent side, tau perpendicular is the adjacent side, we'll go for cos 60. And if you wanted to view it a different way, you could also, sine 30 is the same thing as cos 60, but I think it's clearer to label cos 60 here. All right, and now we just need the torque on the other side due to the force from the child. And again, that's perpendicular to the R vector, right? If we just draw from the pivot point to where the child's acting, RC there, they're already perpendicular. So we just need to do force from the child times the moment arm, RC. Okay, now we can plug in. We know the force from gravity on the plank is its mass times g, or times 10 meters per second squared. So this will be 10 kilograms, the mass of the plank, times 10 meters per second squared. So there's our force due to gravity, times its R vector, which is labeled for us. Well, we need to figure that out. Okay, so the gravity acts at the center of mass, right? So the plank is 2 meters long. We're given that the plank is 2 meters long. And so the center of mass is 1 meter, or right in the middle, like 1 meter from the end. So 1 meter from the end, if we draw that on the plank here, if this from the left end to the pivot point is 1.5, and gravity is acting 1 meter from the end, then that means the distance between where gravity is acting and the pivot point is 0.5 meters. So you should be able to see why that's 0.5 meters there, and you can see that it is equidistant from the force of the child. It's not super important right now, but R is going to be 0.5 meters. Okay, now we have the tension force. So we don't know what the magnitude of that is, what T is. That's what the question's asking, so we'll just leave it as T. RT, the distance away, is 1.5 meters. That's given to us in the problem. And then we have cos 60. And then on the other side, we have the force from the child. So the child weighs 30 kilograms. So this will be 30 kg times 10 meters per second squared for the force. And then its distance away is 0.5 meters. And there's our whole torque balancing equation. The only unknown is T right here. So we can solve for that. 10 times 10 times 0.5, we'll get, 50 Newton meters here. So kilograms times meter per second squared is newtons, times meters is Newton meters. That is our unit for torque. And so plus T times 1.5 meters times cos times cos 60 equals, and then 30 times 10 times 0.5 is 150 Newton meters. So we can subtract 50 from both sides and divide, and we find that our tension force, the magnitude of it, is just going to be 100 Newton meters divided by 1.5 meters times cos 60. So the meters are going to cancel, and we'll be left with just newtons, and this comes out to 133.33 repeating, or just 0.33. We'll leave it as newtons. And that is the magnitude of the tension in the rope. And so we didn't actually really need to use the force balancing for this problem. But let's say it asked us an extra piece. So we'll go a step beyond. What if it asked us for what this FP is? What is the pivot force here? And like we discussed before, the pivot force is just whatever we need to make the net force equal to 0. So we have to do that separately in the X and the Y direction. So because F net equals 0, that turns into F net X equals 0, and F net Y is also equal to 0. So let's do the X direction first. In the X direction, if we go back to our other page, we see that the only two forces that have an X component are the tension and the pivot force. So the magnitudes of those two have to be equal and opposite, right? The tension points left and the pivot force points to the right. Or if we wanted to say that in terms of just summing them together, we could say that the tension force X component plus the pivot force X component equals 0, which gives us that Tx equals negative Fpx. We know what our tension force is, right? We figured out that it's 133.33 newtons. And if we want the horizontal component, this T parallel, we'll now need to do sine of 60 or cosine of 30. Those are both the same thing. But so Tx is going to be 133.33 newtons times sine of 60 equals negative Fpx. So there's our X component of the pivot force. And we could just move the negative over to the other side, so it's nice and neat. So our pivot force is, of course, pointing in the positive X direction, because the tension force, so I missed that. The tension force points in the negative X direction. So what I should have had here was that the negative tension force equals the negative Fpx. So this middle equation here, this is correct. The tension force is negative, which is why I have this negative sign there. And so we get a negative on both sides, and both of them are positive. Perfect. So we end up with a positive x component of the pivot force, which is what we wanted, which is 133.33 times sine 60, which I don't know off the top of my head, but we're not even asked for it, so I'll just leave it like that. Now for the y component, we have a lot more going on. All of these forces have a y component, right? The tension has T perpendicular that points down, and FG and FC both point down. And then F pivot has a y component that points up. So in the y direction, we'll have T perpendicular, or tension y, whatever we want to call it. Let's call it y because we call the other one x. So tension in the y direction plus Fg, or FGY, it doesn't matter. All of Fg is FGY, so I'll just put the y there to be clear, plus the force from the child in the y direction, plus the pivot force in the y direction equals 0. So now these three here are all negative, right? So less than 0 because they're pointing down. So let's put in the values. Tension is going to be negative 133.33 newtons times, because we want the y component, we're going to use our cos 60. Then force of gravity in the y direction, also negative, and the mass of the plank was 10 kilograms. So here we just have 10 kilograms times 10 meters per second squared. Then we have the child's force. Child was 30 kilograms times 10 meters per second squared. I'm running out of room here, plus FPY, the pivot force in the y direction. So now all these three things are negative, so I can just move them over to the other side, and we'll get that FPY is just the sum of these other three things, which I'm not going to calculate right now. But the magnitude of FPY is going to be positive and equal to the magnitude, again, of the sum of the other three forces in the y direction, so that the total force cancels out to equal 0, and we'll find that the pivot force has a positive x and a positive y component, just like we found with this arrow that points up and to the right. If we wanted to, we could find the magnitude and the direction using the Pythagorean theorem and inverse tangent, but I will leave that as an exercise for you if you would like.